In this video, we're looking at rational functions. So one of my phrases I like to say is if we take the word rational and we shorten it to ratio, ratio is a fancy way to say fraction. So a rational function is going to be a quotient. It's a fraction of polynomial functions. So that means we're going to have a fraction with variables in the numerator as well as in the denominator. So anytime we're dealing with variables in the denominator, we're going to run into domain issues. So the domain of a rational function is the set of all real numbers except the x values that make the denominator 0. Remember, that's our biggest problem in math. We can't divide by 0. So those are the issues we're going to run into with domain. So let's say I've got these functions here. For a, we've got f of x is x squared minus 9 over x minus 3. Again, if I'm just asked to find the domain, the only thing I'm considering right now is the denominator. And so the fact is my denominator, x minus 3, cannot be equal to 0. That's the one issue we have. So if I add that 3 to the other side, our domain here would be that x cannot be equal to 3. Similarly with b, x squared minus 9 cannot be equal to 0. Now you can solve this two different ways. This is factorable, it's a difference of squares, but you could also solve it by taking square roots. So if I add that 9 to the other side and then take the square root of both sides, I get x can't be equal to plus or minus 3. Now with c, we've got x squared plus 9 can't be equal to 0, but now I need to subtract the 9. So I've got x squared can't be equal to negative 9, and that's actually a true statement. If we're considering just our real values, when we square something, it can never be equal to a negative number. So I have no issues here. This denominator can never be 0. It doesn't matter what number I plug in for x, it's going to get squared, so it'll become positive. And then when I add 9 to a positive thing, it's going to stay positive. So since this has no domain issues, our domain would be all real numbers since there's no problems. Now, the most basic rational function is called the reciprocal function. Again, the most basic type we call the parent function. So our parent function here is just the function 1 over x. Parent functions have no other numbers being added or subtracted or multiplied to them. So the denominator of this function is 0 when x is 0. So our domain here would just be that x cannot be equal to 0. So we kind of want to see what this graph is doing as we get close to 0. So specifically, we're going to start by approaching x values of 0 from the left. Okay, so you can see we've got a table here that lists some x values coming from the negative direction, coming from the left. And as I get closer and closer and closer to 0, I'm getting a y value that's becoming a bigger negative value. So we'd say that as x approaches 0 from the left, we can see from the table and from the graph, the function values, f of x, we'd say decrease without bound. They're going down and they're going to continue going down. So we'd say f of x approaches negative infinity. And so symbolically, we're going to have it look like this. Okay, so we'd say as x approaches 0 from the left, f of x goes to negative infinity. So this might not be any notation you've seen before. So when we have that superscript, that higher up, kind of like an exponent of the minus sign, the negative sign, we'd say from the left. So this says as x approaches 0 from the left. Same idea, let's now approach from the right. Okay, so again, I'm picking x values you see in the table. Those x values are getting closer and closer to 0 coming from the right. And now my y values are getting really big in the positive direction. So as x approaches 0 from the right, the function values now are increasing without bound. So we'd say f of x approaches infinity. So similar notation here. But now we have that little plus sign, which means from the right. So as x approaches 0 from the right, f of x is going to positive infinity. So with these, we were looking at what was happening close to our domain issue. We can also check our end behavior, what's happening as we approach really big x's and really small x's to the left and the right. So we're seeing what happens to the function values of 1 over x as x gets farther away from the origin. And so you can see as our x values get really big, our y values end up getting really small. They're getting really close to 0. Those decimals there, both the negative and the positive, they're both still really close to 0. So it appears that as x increases or decreases without bound, the function values are getting closer to 0. So again, this is talking about end behavior. And in this case, both as x goes to positive infinity and as x goes to negative infinity, our y values are getting stuck by that horizontal asymptote, which is happening at 0. So this is just reiterating that notation of approaching from the right and approaching from the left, and then saying as x goes to infinity or as x goes to negative infinity. So something you're going to see that happens with these domain issues is vertical asymptotes. So a line x equals a is a vertical asymptote if f of x increases or decreases without bound as x approaches a. Now an asymptote we're going to get infinitely close to, but we're never actually going to touch it. So how do we find where those vertical asymptotes appear? Okay, so let's say we have a rational function that have no common factors, and then our zeros of the denominator are going to be vertical asymptotes. So the way I like to say it is vertical asymptotes are factors of the denominator that don't cancel. So let's say we've got these functions here. So that means we're not going to just factor the denominator, we're also going to need to factor the numerator to see if things are going to cancel. Now in A, we've got x over x squared minus 9. So our numerator doesn't factor, but our denominator is a difference of squares. So we can factor it to x plus 3, x minus 3. Now since nothing cancels, that means both parts of our denominator are going to give us vertical asymptotes. So we'll have vertical asymptotes at those two lines at x equals 3 and x equals negative 3. Now, because these are lines, you do need to make sure to use the x equals notation. They are vertical lines, so we need to make sure to label them as such. With B, our numerator has changed, but our denominator has stayed the same. So we can still use our difference of squares to factor in the denominator, but notice this time I have a common factor. I've got x plus 3, both in the numerator and in the denominator, which means this can simplify to 1 over x minus 3. So our vertical asymptote is whatever's left over that didn't cancel. In this case, that's the x minus 3 factor. So our vertical asymptote would be at x equals positive 3. And then with C, from what we talked about with domain, we should already know x squared plus 9 isn't going to factor. It gives imaginary solutions, so it's not factorable in our reals. So in this case, nothing cancels, so this would have no vertical asymptotes. Now, you might be wondering, well, what happened to the piece that canceled, right? Because that's still a domain error. We still had it as a domain issue when we had used that expression previously. Well, it does something different. So a value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. There is a hole corresponding to x equals a and not a vertical asymptote in the graph of a rational function under the following conditions. The value a causes the denominator to be 0, but there is a reduced form of the function's equation in which a does not cause the denominator to be 0. So what that means is, oops, I went my highlighter. Holes are factors of the denominator that do cancel. So what we can do is we take the original expression and we factor it. The pieces that cancel allow us to write a simpler function, a function that's going to behave exactly the same way, but without having the hole. And so what we can do is we can actually find out where the hole would be located based on that simpler function that has the same behavior. So we can find the value of a hole by reducing the fraction and plugging in the x value where the hole occurs. So if we look at the first problem over here on the left, we've got x plus 2 over x squared minus 2x minus 8. So we need to factor in our denominator two numbers that multiply to get to negative 8 and add to get to negative 2 are negative 4 and positive 2. So I can see that I will have these pieces that cancel. And so I'm left with 1 over x minus 4. So from this pieces of information, I know I should have a hole at x is negative 2, because that's the term that canceled. And I'm going to have a vertical asymptote at x equals 4, because that's the factor that's left in the denominator. But we're going to take this a step further, and we can actually find the coordinate where that hole would appear. So what I can do is I can take this simpler function, this reduced fraction, and I can plug in that x value into this function and see what my output should be. So this becomes negative 1/6. So my hole is really the coordinate negative 2 and negative 1/6. Now I want to show you what this looks like on a calculator. Okay, I've already got the original function plugged in. So it's going to graph in blue, and then directly after that, it's going to it's going to graph the simpler function that we created after we simplified. So if I hit graph, you'll see it's going to have those two separate pieces. That's what happens when we have rational functions. And you'll notice now when I graph the red one, it looks identical. But if I take the time here, we'll see if I can get my fingers to work here. All right, we got to get my keyboard. Gets a little finicky. Need my mouse. There it is. All right. If I look at my table, okay, you'll notice that with the original function in blue that we graphed, it has an error when x is -2, and it has an error when x is 4. Okay, those were the locations of the hole and the vertical asymptote. They're problems in the original function. But if you look at -2, when we graphed the simpler function, it has now an x value. So it looks identical. You see all of the other points are identical, but now we know where that hole should have been with that simpler function. And if you check, that is that value is -1/6, which is what we had said with our calculations. So we can do this again with the next problem. So x squared minus 9x plus 20 over x squared minus 4x minus 5. Two numbers that multiply to get to 20 and add to get to -9 would be -5 and -4. And in the denominator, two numbers that multiply to get to -5 and add to get to -4 would be -5 and +1. So again, we have this cancellation of common factors. And so we come up with this simpler function that's going to behave the same way. So now we see we're going to have a hole at x is 5, because that's the factor that canceled. And we'll have a vertical asymptote at x is -1, because that's what's left in our denominator. But we're going to take it that step further and figure out where that hole would be. So I'm going to plug in my value of 5. Trying to be a good color. For x, so 5 minus 4 over 5 plus 1. So 5 minus 4 is 1, 5 plus 1 is 6. So our hole is actually the coordinate of 5, 1/6. And you can check that by graphing in your calculator if you'd like, the same way I've done with the two graphs together. So we're also going to have horizontal asymptotes. So these are our horizontal guidelines that dictate the end behavior. So sometimes they can be crossed. They're not as strict as vertical asymptotes because they're not coming from domain issues. So they can be crossed, but it is going to tell us what the behavior is going to be on the far left and the far right of our graphs. So how do we find horizontal asymptotes? Okay, the key lies in the degree. So it says the degree of the numerator is n, and the degree of the denominator is m. So we're always going to be comparing the degree. It says if n is less than m. So if the numerator has a smaller degree than the denominator, spelled it wrong, denominator, then our the x-axis, or y equals 0, is going to be the horizontal asymptote. So something like x squared, stop. There we go. Something like x squared over x cubed, numerator smaller degree, it's going to be at y equals 0. Now, if they have the same degree, you are going to make a fraction out of the coefficients. So it'll be y equals a fraction of the coefficients. Now, these all, again, need to be labeled properly. So these will all be y equals, being horizontal lines and running into the y-axis. So it's going to be a fraction of the coefficients. Now, if the numerator is greater than the denominator, there's not going to be a horizontal asymptote. Okay, there is going to be something else that's happening, and we'll see that in a minute, but it's not going to be horizontal. It's going to end up being kind of crooked. So if we're tasked with just finding horizontal asymptotes, which is what we're doing first here, the first thing we do, again, is we're going to look at the degree. So for horizontal asymptotes, we look at the degree, our biggest exponent. So in the numerator, we have an invisible exponent of 1. The denominator, our exponent, is 2. So if the denominator is a bigger degree, it's at y equals 0. For b, Now when I compare the degrees, they're the same. Numerator degree 2, denominator degree 2. So I'm going to make a fraction out of my coefficients. So that means I have 4 over 2, which just reduces to 2. And with C, when we compare a degree, the numerator is degree 3 and the denominator is degree 2. So this one is not going to have a horizontal asymptote. So what happens is if it's not horizontal, it ends up being what we call a slant asymptote. So in general, if we have a rational function that have no common factors, and the degree of P is 1 greater than the degree of Q, if your numerator is 1 degree bigger than your denominator, we're going to have a slant asymptote. And we can find the slant asymptote by dividing. So do a normal division. And what happens is the equation of the slant asymptote is obtained by dropping the term with the remainder. So since we're 1 degree bigger, once we divide, we should end up with something degree 1. It's going to be linear. And so it'll look something like this, and then with a remainder. So we basically just drop the remainder part, and what we're left with becomes the equation of the line. That would be the slant asymptote. So we've got x squared minus 4x minus 5 over x minus 3 that we're trying to find the slant asymptote. The degree of the numerator is 1 degree bigger than the denominator. Now, luckily for us, our denominator is itself linear with a lead coefficient of 1, which means we can use synthetic division here. So remember, when you're doing synthetic division, the number we put in the corner is the 0 of the factor. So if we've got x minus 3, the 0 of that is positive 3. I'm going to grab the coefficients, 1, negative 4, negative 5, and then we're going to divide. So I bring down my 1, multiply in the corner to get 3. We add down to get negative 1, multiply in the corner to get negative 3, add down to get negative 8. But again, I'm going to ignore the remainder. I'm going to take just what's left here, which is my linear term. My slant asymptote is going to be at the line y equals, that would be 1x. So I just have x and then minus 1.